All right, folks, we're going to work on the next exercise in chapter 5, which is one of the game zone exercises. It's in a separate section than the regular programming exercises. And I always find these kind of a lot of fun. So for a lot of us who are into coding and computers, it's often, the byproduct of being a gamer, right? Or being interested in gaming and, hey, I kind of like to learn how to do this, right? That kind of mentality. But games are really kind of interesting when you try to code them because they're connected to something that's kind of real. So for example, like if I'm to write like a chess program, for example, well, now I'm connecting it to something that happens in reality that has like rules and limitations and a process that, like playing chess is like a thing, right? You have to have a board, you have to have the players, and there's like the white pieces and the black pieces, and they move certain ways. And how do you keep track of where everything is? Think of the complexities that are involved in even a simple game like, chess or checkers. Same kind of thing happens with a game like rock, paper, scissors. And this is kind of an interesting thought, right? Because if you were sitting in a room with a couple of like 5-year-olds, right, that know how to play rock, paper, scissors, they, in their very primitive mindset, could very easily tell you, yeah, there's 3 things you do. You have a fist, that's the rock, flat hand is paper, you go like this with your fingers, and that's scissors, right? And when you're doing that, right, I want you to think about this. These 5-year-olds are able to explain to each other on a very primitive level how to play rock, paper, scissors, right? And what are the rules for it? Well, okay, so it's like if you put 2 symbols in there together. So if you guys don't know, I'm assuming you do, but you have 2 people playing and you do a count to 3. You go 1, 2, 3, right? And if you guys are watching my video window, right? And if you both make a fist, you both are claiming rock. Well, that's a tie because they're both the same thing. So you just do it again. It doesn't count. Now, if you put up different things, one person puts up a rock and one person puts up a piece of paper, the rules of rock, paper, scissors say that a piece of paper covers the rock, so the paper wins. Or if one's a rock and one's a scissors, right? Rock breaks the scissors, rock wins. Or if it's paper and scissors, scissors cuts paper, scissors wins. So there's a scenario where all 3 of them win, right? If you feel where I'm going with it. And what might be helpful, and I'm just kind of, showing you how my brain works on this kind of goofy stuff, is like if you want to like kind of figure out all the possible scenarios. So this makes you think. It goes, okay, all right. So the 5-year-olds get it, right? So they just go 1, 2, 3. I got rock, you got paper, and then sometimes they go best of 3, 2 out of 3 or something like that. But they figured it out in like 2 minutes, all the logic of the game and how to play, right? So one 5-year-old described it to the other, but now you got to code it as a programmer, and all of a sudden it's like, oh, how do I do that? Right? I mean, really, it's not necessarily an easy process. So what I'm doing here is I'm just pulling up a spreadsheet. And you're like, what the hell is he doing? Right? Well, I'm trying to show you that there's possibilities that happen, and that you're either winning or tying. So you have player 1, right? Or how about this, right? We're going to be playing against the computer is what we're going to do. So one of the players is a computer and one of them is a human, right? And so what are all the possibilities that could happen? This is, what you have to think about. So it's possible that the computer could pick rock and the human could pick rock, right? What's the result, right? So this column would be called result. So what would be the result of that? Well, that's a tie, right? So play again, basically. But if the computer chooses rock and the human chooses scissors, who wins? Computer wins, right? What if the computer chose rock and the human chose paper? And really, I should probably, okay. So it's rock, paper, scissors, right? So let's do paper here. So the computer's always picking rock right now, and the human's picking rock, paper, scissors. And in this scenario, paper covers rock, so the human wins, right? Well, that covers one set of possibilities, it covers all the possibilities for computer choosing rock, but the computer could also choose paper. And you know what? There's three possibilities with that too, right? So we do that 3 times. And then of course, there's scissors, and that could happen 3 different ways too. So what we're doing here is we're creating basically a chart of like what happens in every possible scenario. And I don't know if you guys are picking up on this, but we're kind of creating like a logic matrix, here. Oops. And really what I meant to do there is copy all that. And if you watch my videos, I think I do my chart a little bit differently. But the whole point is that you look at every possibility. How many possibilities are there? Well, when we analyze it, there's 3, 6, there's 9 possible combinations in this game, right? And then, okay, so who wins here? Computer wins. Who wins here? It's a tie. Who wins here? The human wins. Who wins here? Human wins. Who wins here? Computer wins. Who wins here? Nobody. It's a tie. So those are all the possibilities that are possible, right? Not to sound silly about it. And for as goofy as that this is, it gives me a roadmap to look at for all the possible game scenarios that could occur. Okay, now I want you to think about this really carefully. This is rock, paper, scissors. This is a really super simple game. It's almost as simple as tic-tac-toe, right? Can you imagine the algorithms for chess? Like, okay, like just like plotting how a horse moves, and then where does it land? Is it landing on a piece that's open? Is it landing on a piece? Can it take the piece that it's landing? And if it takes the piece, is it checkmate? Or did it fall off the board? Think of all those scenarios. It's crazy, right? But people yet have figured out that logic very systematically. And you know what? You can go out on the internet and find the code if you want. It's not that hard to find, right? Okay, so here's all the possibilities, and now we have to write code for this. All right, so how do I possibly even begin to sketch this out? All right, so here's how my brain works. I'm going to do something really super ultra goofy. Is I'm going to bring up my Notepad++, right? I'm not going to use it to code with. I'm just using it because it creates a white screen, right? And I don't want to use the whiteboard tool in Zoom. And no offense to the Zoom people, but I find it really cumbersome. And it's easier for me to put this on screen and draw over it with my annotation tool than it is to do something else. But basically, when we learn how to write computer code, you also learn about the process of pseudocoding. Now, once again, if you took the Python class, especially if you took it with me, I do a whole thing on pseudocoding, right? Like we do the recipe thing where we talk about, solving problems sequentially in the order of them and having inputs, outputs, and processing. And then we also learn that the shapes that we use when we create a flow chart, which is a visual representation of pseudocode, that we basically use like 3 or 4 different shapes. The one shape is a regular rectangle, and this is for input or output. So in other words, we're either asking the user to add something or we're putting something on the screen. The other shape that we use, and actually, I apologize, this is incorrect. Let's redo this. The parallelogram, and that's a horrible parallelogram. It's like a rectangle that's tilted, right? Okay. Should we try? Do they have a tool for that? No. Sorry. All right. So if I was in a drawing program, I could totally do that. But there's my parallelogram. Parallelograms are for input and output. You're interacting with the user. You're asking for something or you're showing them a message. When you actually do calculations or math or programming steps, the user doesn't need to see. Those go in rectangles. So it's just just think of it as, code behind the scenes, right? Like people don't need to see what math is happening in an application in order to know it's working, right? That's a process, right? Then finally, when we start to like have maybe a series of steps, we use like arrows to show the direction of flow of a program. In other words, this happens first, then you go to this one, then you go to that one. When you hit an if statement in programming code, we do that with a diamond shape, right, like this. And then we ask a question that's true, false, right? So we ask a true, false question, and the result's going to be, it's a Boolean, the result's going to be true or false. And what'll happen is we'll have one branch that comes off. This is what happens when it's true. And then this is what happens when it's false. And then on this line here, we have more programming code. It could be input, could be output, whatever. And then you can either have a step in here or you can skip it. So sometimes you don't have to have something in there, and sometimes you do, right? So this might be a whole separate series of steps that happen. This might be another series of steps that happen. And you know, sometimes you make a decision and you get a true false answer, which just leads to another question, right? All right. Kind of like the question of like, hey, do I have more than $20? True. Well, I can order a pizza. And then you're like, well, wait a second. If I have more than $20, maybe I can order submarine sandwiches instead, you know, something I want more, right? Which would be a separate decision that happens after the fact. So this is kind of the lay of the land in terms of how we kind of sketch it. Now, okay, why do we bother sketching? Because when you get to a more complicated problem, it is really hard to think it through in your brain, all the scenarios. The Excel spreadsheet that I did, that was just one tool I used to show all the possible combinations and what's going to happen. So imagine the scenario. The program will start. If it was a well-written program, we'd probably put instructions on the screen. But in this case, we'll just say, play rock, paper, scissors, right? One player will be the computer, which will randomly select rock, paper, or scissors. And then the other player is the human, who will manually select their choice, right? So you're going to prompt the user for input. So you're going to basically start by, start the game, prompt user for choice. So, and the choice would be basically, I'm going to call it RPS, rock, paper, scissors. So I'm going to choose one of those. And because it's easier generally to process numbers, they'll probably enter 1, 2, or 3. Most likely that's what they'll do. Right. We'll capture that input, right? And then compare. Okay, well, actually, prompt user for choice, computer generates random choice. So why do we use numbers? Because when we generate a random value in computer programming, we're always generating numbers. So the computer is going to generate basically 1, 2, or 3. Also, then we're going to compare the computer to the user, let's say end user choices, or maybe that's a good word. And then we start looking at what they chose. Okay, so here comes the chart, right? So why do we do the Excel thing? Because these are all the possibilities. So I can write if statements. So now think about this. If I'm going to have a chart like this, I might say, well, you know what? We'll use the number 1 to represent rock, right? And we'll use the number 2 to represent paper, and the number 3 to represent scissors, right? And then, you know what? The humans are going to do the same thing. So they're going to have basically, well, this is a 1, that's a 2, that's a 3. And actually that pattern is just going to repeat, isn't it? Right? So rock, paper, scissors. Oops. Rock, paper, scissors, rock, paper, scissors. So now we have even a better chart, right? Because now we know the values that we're going to compare. So you could write an if statement next in our program that would say, if computer choice equals 1 and human choice equals 1, it's a tie. If computer chooses 1 and paper chooses 2, the human wins. You see what's happening, right? Now, what becomes interesting about this is if you really start to map this out, right? So I'm going to get rid of Excel here again, right? Compared to the user choices, what would be the next thing that happens here? Well, I've programmed this a number of different times, and you can just follow that chart all the way down, but you can just check to see, and I'm going to use the keyword if computer, let's just say that's the computer, well, maybe we call it computer choice, is equivalent to, let's call it user choice, right? Then it's a tie. Basically, it's as simple as that, right? And so it doesn't, what's kind of interesting about this statement is, right, that one statement actually covers all 3 tie possibilities. So rock, rock, paper, paper, and scissors, scissors just cover. So that's 3 things on the table already gone. 1/3 of the options are already taken care of, right? And so if you look at it like that, then you can come in here and you can, like, notate or highlight, cross it off, or whatever you want to do, but or just take it on faith, basically, that 1/3 of the choices are now handled with one statement. All right. So this is a statement that we're checking, right? And the way that we would code this in Java is this is in parentheses. It resolves to true, false. If it resolves to false, so here's where I'm going to start drawing, right? So this would be programming code in the background. So that would go in a rectangle, right? And then from there, and actually, that's not true. So this statement, it would actually be in a big diamond shape, right? So if you can imagine that. And then if it was true, we output, tie, and the game's done, really, right? You could ask play again, right? But if it's false and we go the other way, well, what happens next? Well, this wasn't, they're not equal. So now you got to check all the other scenarios on the table. So you could say, you'd put a diamond shape in here and you'd say, if the computer choice, so if the computer choice is rock, right, and the human choice equals, well, the ties were already covered, so we would just go to paper, right? Then who's the winner? And so then you go to your output messages, what's true and false, right? So if it's true, you're done again. If it's false, you keep, basically what happens is you keep kind of marching down this branch here because you've asked the one question and that one wasn't true. So you ask the next question and then you go to the next question, et cetera, until all the scenarios are covered. Now, here's what's really interesting about this. And I'm going to see if I know I have like a slide on this somewhere. I'm going to pause the recording just for a second and I'm going to show you a